In topic 5.2, heating effects of electric currents, and also in topic 5.3 on electric cells, we're going to be dealing with circuits, and so we need to be fairly clear on what some of the symbols are that are used for these circuits. And once we've gone through these symbols, you'll then be able to understand how circuits are set up and what the details of the circuit are. So we're literally just going to whip through a few different symbols that are used in electric circuits, what they represent, and in some cases a little bit more detail on what they do, what they are, why they're useful. So the first few that we're looking at here are to do with power supplies. So the first one is a cell, so literally a single cell that produces electricity. A battery is then a combination of cells, so a whole heap of cells stacked one after the other with positive connected to negative. And then the third one to look at is an AC supply, so an alternating current supply, and so that looks like that symbol there. So as I said, all of these three are about providing a circuit with electricity, and they do that by providing an EMF to the circuit. Now these first two in particular, the battery and the cell, they're going to be covered in more detail in topic 5.3 on electric cells, so I won't say too much more about them here. The only other point to add is that an AC supply, being an alternating current supply, usually it's alternating somewhere in the 50 Hz or 60 Hz range, depending on which country you're in. That's if you plug into a wall. You can't produce AC supplies with other frequencies if you've got a tunable AC supply. But ultimately what it means is that the current actually will change direction through the circuit. So on one half of the cycle it'll flow one way through the circuit, on the other half of the cycle it'll flow back in the opposite direction. Moving on to the next symbol is this one here that represents an open switch. So a switch is literally just the sort of switch that you'd flick on a wall to turn a light on. And usually it's represented in the open state. You don't usually represent a switch in the closed state because then it just looks like a wire. In some cases you might see that there's a couple of dots there to make it clearer that it isn't actually a closed switch. Likewise on this symbol you might sometimes see some dots there as well. And so a switch basically opens or closes a circuit. So if it's open it means that no current's going to flow. If it's closed, then it means that current is able to flow around the circuit. Usually when we represent them as open switches, it's just there to show where the switch is located, and so we can be aware of what effect it's going to have on the circuit. But generally speaking, we don't really worry too much about whether it's open or closed when we do circuit analysis. The next two are measuring devices. So they look like this. So one's got a V in a circle and the other's got an A in a circle. And they represent a voltmeter and an ammeter. And hopefully you can identify there without too much difficulty that a voltmeter measures potential difference or EMF. So either of those two, depending on whether it's a source or a component that's using the energy in the circuit. And just as a note, hopefully this is a reminder, a voltmeter is connected in parallel, so it needs to sort of sample the amount of energy before and after a component, find the difference to determine how much energy is being used per coulomb, and so they need to be connected in parallel. The other one then is an ammeter, and that measures current, and in order to measure current, all of the current needs to flow through the ammeter so it can sort of be counted in inverted commas. And so they're connected in series. So there's the two measuring devices. The next one is a lamp. Just skip past a lamp really quickly. The symbol for a lamp is a circle with a cross in it. And as you know, a lamp just converts electrical energy into light energy. The next one we're going to deal with in a fair bit more detail in this topic. It's just a little rectangle. And it's a resistor. As I said, we're going to go through that in much more detail in this topic, so I'm not going to say too much about them here, apart from the fact that there are a few different versions of resistors that you'll see, and the second one there is a variable resistor, so we can change the resistance of that resistor. I will just mention here briefly that the purpose of a resistor is that it dissipates electrical energy as heat energy. Now, when we say that it dissipates, we're not saying that it heats up and becomes hot. We're just saying that it removes energy from the circuit and transfers it to heat energy. So it's not like a heating element that gets hotter. It just removes energy from the circuit in that way. The next one is a special type of variable resistor, and instead of having an arrow through it, it has an arrow pointing down from the top. That arrow could sort of slide to the left, or it could slide to the right, so that point of contact is actually movable, and the potentiometer actually can be connected at 3 points, not just 2 like most electrical components. So it's sometimes referred to as a rheostat as well, so it's another name for it. It divides a potential difference into 2 smaller potential differences. And the way that it does that is that sliding contact on the top. When you move it to one side, you'll find more voltage where you've got the greater resistance. And so if it's in the middle, it'll mean that the potential difference is split evenly. And so it means that you can take a larger potential difference and output 2 smaller potential differences. As I said, depends on the sliding contact point. There are 2 more types of resistors to be aware of here as well, and the symbol basically is always built off this rectangular shape. The next one, though, we have 2 arrows that are sort of pointing towards it. It's known as a light dependent resistor. I think that name's fairly self-explanatory, in that changes its resistance depending on the amount of light that's shining on it. Like I say, fairly self-explanatory, that one. The next one is a thermistor. Now the symbol's a little bit unusual. It's again that rectangle with a line through it and then a bar across the top of it. It's known as a thermistor. A slightly more easy to understand name would be a temperature dependent resistor. So the resistance of this type of resistor depends on the temperature. And again, both of those components would dissipate electrical energy as heat energy. The next type of component is a very different one, and the symbol for it looks like this. So it's sort of a little bit of a squiggle, 2 parallel lines and then another squiggle. What it represents is a coil on the left and then another coil on the right. That's the symbol for a transformer. And a transformer takes an AC voltage and steps it up or down depending on the number of coils on each side. And there's a lot more to be covered about that later. And like I say, it does require an AC voltage. It won't work with DC. The next one is a heating element, and as is fairly obvious with a heating element, it's going to produce heat. So it converts electrical energy into heat energy, but for the purpose of actually radiating that heat energy. So it's a bit different to a resistor. The second last one is a diode. It looks like that, so it's a triangle with a line on it, and a diode is a semiconductor component, so it's made of silicon usually. It only allows current to flow one way through it. There's a lot more that can be said about diodes, but it's not really covered in the IB course. But there will be 1 or 2 moments where we'll briefly talk about diodes and why they're useful. And finally, the last one is a capacitor. So 2 parallel lines separated by a small gap, which reflects the structure of a capacitor being 2 parallel plates. And the purpose of a capacitor is that it stores charge. Having outlined all of those circuit components, I'll just point out here that all of them are in the data booklet, so you can refer to the data booklet to get each of those components and what the names of them are. But it's important to make sure you know a bit about what they're used for as well. The other thing we need to be aware of with circuit diagrams is how we're going to draw them and what the conventions are. when we represent a circuit in a diagram form. And there are a few things to be aware of. The first is that we're usually going to use horizontal and vertical lines to draw the wires that are joining the components. That's just to keep things a bit neat and tidy, rather than using squiggly lines or lines at any particular angle. The second thing is where wires are joined at a junction, we're going to use a dot to indicate that they are joined. So whenever you see a dot, it means that they are actually connected, and where they're not connected, we would have no dot. So if we had wires that were, say, one that's going horizontally and one that comes down, and we draw a dot there, then that means that that point is a point of connection. So it follows then where wires cross but don't join, we don't have a dot. There won't be too many situations where that occurs, because most of the time we can draw circuits separated out, but just to mention that if we don't have that joining of wires, then we'd have that sort of situation. Now, to give you an example of a circuit, let's imagine we had a battery, and connected to that battery was a switch. So on this side we're going to draw our switch. So notice that we don't have to draw them all horizontally, we can draw components to the side, rotated so that they're on a vertical line. We're going to measure the current through this circuit, and the current in particular through a resistor that's in the circuit. So there's the loop of the circuit, so that current will flow through it when the switch is closed, and we're also going to measure the voltage across the resistor as well. So using that voltmeter in parallel, and because these are junctions, we're going to draw those dots in to show that they're joined. It's usually a good idea to indicate the quantities of the components that are in the circuit as well. So let's imagine it's a 6 volt battery and a 47 ohm resistor. So there's an example of a circuit diagram. It's really important to make sure you understand how to interpret them, that you know all the components that are in them, so you can make sense of how current flows through the circuit and where the potential differences are around the circuit and where EMF is being supplied to the circuit.